This is Professor Hill. Today we're going to talk about ocean sediments. Now, off the top of my head, that might sound a little boring, but it isn't. Sediments tell us all sorts of things that we would otherwise not know ever happened. It's like the way that the earth writes its own diary, so that time way before there were humans, the earth was busy writing down in the sediments what was going on. So today we're going to learn about them. How we classify them by size, by their source, how they become sediments, how they get to where they're going, what happens to them at the end, and last but certainly not least, the actual relevance in the real world. What good do sediments or knowledge of sediments actually do for us? There's actually whole branches of studies called sedimentology, which I happen to be very fond of. Okay, so sediments, in case you don't know, are just loose accumulations of particulate matter. In this case, little teeny tiny bits of shell or sand or silt or clay, stuff like that. Being humans, we like to classify things, and we do it by size and by source. So we're going to talk about size first, because that's the easiest. So sediments that are categorized by size tend to be clastic or detrital. That just basically means that they are a loose collection of inorganic matter. Inorganic means it never used to be alive. So it's basically broken down pieces of rocks or minerals. So if we're classifying these detrital or clastic sediments, and I don't know why it is, but in geology very frequently we have two words for the same thing. I'll just give them both to you, so if you're doing the reading and they use the other word, you'll know what they're talking about. So to classify by size, there's four basic sizes that you should all know. From smallest to largest, we have clay, then silt, then sand, then gravel. There are sizes for these sand, silt, clay, and gravel. Now notice that I put a few extra sizes in here because we got clay down there, but there's smaller things than clay, all right? There's a lot of smaller things than clay. And there's bigger things than gravel, a lot bigger things. But these are the main ones. I put the ones in orange that you see most in the ocean. Notice that colloidal is so small that it's less than a micrometer. What's a micrometer? It's 1/1,000,000th of a meter. So a meter, you know, is about this long, right? If you could divide it into 1,000,000 pieces, a micrometer would be less than one. So you can't see colloidal sediment. Clay sediment, you really can't see clay sediment either by itself, not one little piece of clay sediment, because it's less than 256th of a millimeter. I don't know if you know how big a millimeter is. It might be about as thick as your thumbnail. So if you could divide that into 256 pieces, one of those would be clay size. Now, in this picture here, you see someone standing in clay with their boots kind of stuck. If you've ever walked through clay, wet clay, it's very adhesive, right? It sticks to things. If you've ever made things out of clay, it sticks, right? And you can change it. If it was dry and I had a handful of it and I dropped it in the wind, you'd see the sort of dust flying away, but you wouldn't see one piece of clay. The next bigger size is silt. For that picture, we have some murky water because you could kind of see silt. We're getting a little bit bigger, up to 1/16th of a millimeter, right? So take your thumbnail, divide it into 16 pieces. One of those, that would be a big piece of silt. The way actually geologists tell the difference in the field is you put a little bit in your mouth. If you can feel the grit, it's silt. If you can't, it's clay. Sort of like here in the desert, if you cross the road and there's a tractor on one side, right, and the dust flows through your car window, if you had your car window down, if you can feel grit in your teeth afterwards, that's silt. If you don't feel anything, you probably have clay in your sinuses. Okay, sand. You think we know sand, right, because we live in the desert? That actually varies quite a bit. You know, you start at the 1/16th, that's very, very fine sand, goes up to 2 millimeters. Gravel is I think they should say less than. I think it should say less than. I'll have to look that up. But gravels are about 64 millimeters, which is about this long, right? A couple inches. Cobbles are a little bit bigger than that, right? And boulders are something pretty much over 30 millimeters, 256 millimeters, sorry. I meant 30 centimeters, which is actually wrong too. That'd be 25 centimeters. Anyway, anything about this big and bigger is a boulder. Okay, but those four big sizes you should know, and you should know which is the smallest and which is the largest. This is just to help you visualize, right? If you had a big fat piece of sand, the biggest piece of sand you could have, 2 millimeters, it would be this big yellow round thing. And then medium sand would be this green circle. Fine sand that's only like a 1/16 of a millimeter would be this little blue one. Silt is much smaller than that. And clay, you can't really see it, but there's a little tiny dot right there. Just to help you visualize. Okay, so that's how to classify sediments by size. If you want to classify them by source, where they came from, we have quite a few places they come from. The most of our sediments in the ocean come from inorganic sources, meaning they used to be rocks and now they've been broken down into smaller pieces. Organic sediments mean they used to be alive, basically seashells that have been broken down. We have hydrogenous ones. That means they came out of the water. There's a couple different ways that could have happened. I'll explain that in a minute. Volcanogenic? I don't say that word very often out loud. I think it's volcanogenic. Anyway, basically the stuff that rains down from the air after a volcanic explosion, because it goes up in the air, it doesn't stay there forever, right? It ends up falling out of the sky, and a big one, will end up in the sediments of the ocean floor. Cosmogenic. I don't usually say these words out loud, and it should say prionic, but cosmogenous would work too. Anyway, that's basically space dust. Okay, we get quite a bit of that every day. Stars tell you basically where we get most of our sediments in the ocean. Okay, so let's start with inorganic, right? That means usually it came from the land. It could have come from rocks that are created at the mid-ocean spreading ridge, but most of it comes from the land because we have mountains and cliffs, and we have water and rain and all sorts of things on the land that break rocks down and bring them to the ocean. So these piles of sediment at the base of these cliffs, where do you think that came from? It came from these cliffs being worn down. So these terrigenous sediments or inorganic matter basically comes from weathering or the erosion of rocks, and we'll go a little more into that later. Okay, organic sediments, like I said before, that in this class that basically means it used to be alive. They're made out of seashells, and we're going to talk about two kinds. And there's not too many chemical equations you need to know in this class, but you do need to know these two. Silica, which is silica, Si is the abbreviation for silica, and oxygen. So SiO2, that's our chemical formula for silica, and calcium carbonate, CaCO3, is the chemical formula for calcium carbonate. Both of those particular chemicals are really good for making shells. And so we've got a lot of organic sediments made of silica or calcium carbonate. Okay, let's talk about the silica ones a little bit. Silica, there's a lot of things to say about silica. I'm trying to decide where to start and what to leave out. Silica, what we got here is radial areas. They're little micro predators. If you're a Star Trek fan, you might notice they look a little bit like Klingon battle cruisers. They're, again, the little predators of the microscopic world. They're made of silica. Silica is the same thing that is used to make glass and is present in lots and lots of sand. It's very, very hard stuff. That's one thing you should know, how it differs from carbonate. It's harder. There's diatoms. They're a sort of a plant-like thing, microscopic, that also uses silica in its shells. And there's lots of kind of diatoms in the world. In fact, this is a picture of many, many, many microscopic diatoms that died and ended up on the bottom of the ocean and in something called diatomaceous ooze, and it eventually made a rock, and that can be mined and used for other things. Oh, they're showing you, by the way, this is a pencil for scale, right? So you can see that the dust that comes off of them is very small, and each one of those, I'm sure, there's got many, many diatoms on it, because again, they're microscopic. Okay, calcium carbonate, much softer than silica. It dissolves in weak acid very easily. This is a big favorite with a lot of the phytoplankton, microscopic plants that live in the ocean. These particular microscopic plants are called coccolithophores. I'd never ask you that on a test. We have a scale down here. This little bar is 2 micrometers. So again, take a meter stick, divide it into 1,000,000 pieces. Can't even imagine that. 2 of those would be this long. So these guys are only like maybe 5 micrometers apart. So they're, again, you can't see them. And there are so many kinds of phytoplankton that make their shells out of calcium carbonate. Just showing you a few pictures. And the reason that they're an important part of sediment is that there's so many of them. This is a picture of red tide up here. It's an algae that uses calcium carbonate as its shell. And you can see it, well, because it's red and because there's so many of them. This picture here is showing you the coast, southern part of the UK. And this is a photo from space. And this cloudy stuff you see in the water is a big algal bloom. It's when nutrients upwell, and then there's a huge blooming, as they call it, of phytoplankton for a while. And then they die after a few days and end up as sediment on the bottom of the floor if they're not eaten. You can also have macroscopic calcium carbonate, because a lot of the bigger shells also tend to make, bigger animals tend to make their shells out of calcium carbonate. So you'd end up, you see that rock on the right, that's called coquina, when you have a rock that just looks like its shells pressed together. But fecal pellet shells, a lot of oceanic things are made out of calcium carbonate. They end up on the ocean floor, they get pressed together, and they become what we call carbonate rock. They're showing you pictures of this to indicate that there might be fossils in there. So these creatures live and they die, and if they're not eaten, they drift down through the water column. That constant drifting down through the water column of these tiny creatures is called marine snow. This picture is inaccurate in that you wouldn't see this because, like I told you before, these things are very, very tiny. But who knows what they did to make this picture, to give you the idea that marine snow is always happening. And so sediment is always accumulating on the bottom of the ocean. And remember, that was one of the reasons that they were arguing about whether the earth is old or young, because they said, if the earth is old, how come the oceans didn't fill up with sediment? And what was the answer to that question? Well, plate tectonics. That sediment gets recycled when they end up in convergent zones and they subduct. The crust subducts. All right, deep sea oozes. So this marine snow with these little tiny microscopic creatures ends up at the bottom of the ocean floor. And we oftentimes call them oozes. Silicious ooze for the silica creatures, carbonate ooze for the calcium carbonate creatures. As it says here in the middle, the definition of ooze is fine-grained, very small pieces containing more than 30% biogenetic material, meaning 30% of things, a third of it used to be alive. So basically itty-bitty little seashells, right? Why do these accumulate in the deep ocean basins? Why? Because they're very calm. Not a lot of currents going on. If you're so tiny that, any current at all would blow you away, you aren't going to settle out until you're in a really super, super calm area. Again, oozes are in the clay or colloidal size. So they're either less than 4 micrometers to less than 1 micrometer. So very, very fine stuff. This is a 70s map giving you a very general location of oozes on the ocean floor. So let's start with the diatoms. Okay, I told you they were a subcategory of siliceous oozes. We got a lot of them around Antarctica because there's a lot of upwelling and a lot of algal blooms there, especially during the spring. Here's some radiolaria blooms areas. Those are mostly around the equator. Calcareous, right? The calcium carbonate, that's most of the ocean. That's the favorite shell, right? Abyssal clay. Now, what does that mean? Abyssal means, that, you know, the deep sea plains. Clay, now we're talking about a size. So we're no longer talking about a biological component. We're talking about a size. So basically things that are really tiny that got washed off of the continents and ended out in the ocean. And then continental sediment. So that's gray. So basically the stuff that just comes off the continents, it's not necessarily that small yet. And it just sort of ends up plopped on the continental shelf around the continents. This is really neat. The oceanic sedimentation rate. Okay, now near shore, this is different, right? Stuff is coming off the continents, and I've already showed you before on Google Earth that the continental ridge, the continental shelf, is very thick. It's much shallower than the deep ocean because it's made of basically the inorganic materials that are coming off the continent and also the shells that are out there near the shore, and that's where most life is. And so it's much thicker. Okay, so we're not talking about that. We're talking about out in the deep ocean, the sediment rate. Okay. Sorry, I guess I was wrong. The continental shelf. So the continental shelf is, again, much faster rate than the abyssal plain. So 10 to 40 centimeters every 1,000 years. So 10 centimeters would be about this much, 40 would be about this much every 1,000 years. Now that's actually seems pretty slow, right? But geologic time is big. So I have these pictures here of the White Cliffs of Dover. The White Cliffs of Dover are chalk, and they're made up almost entirely of coccolithophores. And I told you coccolithophores are about 5 micrometers big. And that's about 350 feet of them. Of course, that used to be underwater. That was part of the continental shelf. We'll talk about that in a second. But think about that, you know, 5 micrometers big. It only accumulates 10 to 40 centimeters every 1,000 years. And there's 350 feet of it there. That's an amazing amount of time. And of course, there's probably more where we can't see it beneath the beach. Now, back to, if this is collected on the continental shelf, what's it doing up above the waves? Well, back to plate tectonics again. This is the southern coast of the UK. Let me show you. No, wait, I don't want it to stop recording. Got to make sure it's not stopping recording. Continue recording. Okay, good. All right, so let's go over to the UK. There we are. All right, so let's get our north and back out a little bit. All right, so southern coast of the UK is up here somewhere, right? This is the UK. White Cliffs of Dover are down here. They used to be part of this continental shelf, which you can still see, right? But why? What pushed them up? The only thing that could push up just big, huge masses of land, plate tectonics. So what's going on here? Well, Africa, the plate that has Africa and the ocean around it, is heading north. It's slowly closing off the Mediterranean Sea, and its force can be felt all the way up here, hundreds of miles north, and it's pushing some of the rock on the continental shelf out of the ocean. Pretty cool, hey? It's really amazing if you think about it. All right, so then That's the speedy rate, 10 to 40 centimeters every 1,000 years. And let's switch this. No, wait. Continue. I almost screwed up there. Let's move this down. Hope I didn't close it off. Okay. Well, I do need to view it differently, but I'm not sure how. Okay. Add-ins. I haven't stopped recording. Okay. Display settings, swap. All right. Okay. So, continental shelf, 10 to 40 centimeters per 1,000 years. The abyssal plain, 1/2 to 1 centimeter, a centimeter, probably about the thickness of my finger, 1/2 of that to one of these every 1,000 years. That's how slowly sediment accumulates way out in the deepest parts of the ocean. So like I said, that marine snow thing, that was totally inaccurate. You would not see it. Very slow. Okay. Hydrogenous sediments, also known as precipitate or authigenic. That means they're formed in their present position. There's one main way that happens is basically by evaporation. So this is a picture of the world back at a different time period. You can see that the ocean was much higher. The middle of the United States is completely flooded, and there's probably no ice on the planet, and that's probably why. And so in these areas where there's eventually going to be land, because we know, right, that this is now land, and this is now, all these places are now land. What happens is that as the land rises or the sea retreats, you get areas that are drying out. Now around here the water is very hard. Water in the sea is even harder, right? It's got salt in it, it's got all sorts of things in it, but the main thing it has in it is table salt, sodium chloride. As it dries out, that stuff can't stay in solution anymore, and it precipitates out. Okay, like Great Salt Lake. That is a glacial lake that has been drying out for about 30,000 years. And now it's sort of famous because you can't, you can float in it even if you can't swim, right? Because it's got so much salt in it now. It's been drying out, and the salt is getting more and more concentrated as the water disappears to evaporation. That happens out here in the desert periodically in a lot of different ways. And this picture on the right here is showing you something called anhydrite, which is coming out of water that has run off the mountains in a desert, you know, during one of our very infrequent huge storms. You can sort of see it's a desert by looking at the mountains. There isn't a lot of vegetation, and so you get these desert storms, and the water accumulates in these areas. They're called playa lakes, and then they dry out and they leave behind the minerals that were in them. So you can get salt, and you can also get gypsum. Those are the two main precipitates that get out of water. This is just kind of a schematic of how it works. Another way it can work in tidal pools. We have water can come in a tidal pool, and usually there's some kind of restriction. The tidal pool is deeper than the beach, and there's a restriction so that when the tide goes back out, sometimes the water is trapped in here. And what happens is, it's a beach, if it's a sunny day, right, and if it's a hot beach, the water evaporates and it gets saltier and saltier. And this is showing how that if it gets too salty, right, it'll kill the animals in it. But the salt, once it gets too salty, it'll start to precipitate out of the bottom. Another way to think about this is if you make a glass of Kool-Aid maybe, and you stir in too much sugar, right, you put in the powder, that dissolves. You put in the sugar, that dissolves. If you put in too much sugar, it'll precipitate back out of the bottom. You'll have sugar sludge on the bottom. Or if you set that glass of Kool-Aid out in the parking lot in July in Yuma, eventually all the water would go away and you'd have some kind of pink-white powder at the bottom. It would have precipitated out. That's the same way that sediments precipitate out of the ocean. This I'm just going to mention because it's cool. It's another hydrogenous sediment that precipitates out at an extremely slow rate. I actually have one, which is amazing that I do. They're probably one of the rarest things on this planet. Well, maybe not that rare, but they're very hard to get because they form out in the abyssal plain. Basically, minerals precipitate out of a loci that gives them a base to start out on. And then they just sort of grow there. But they grow at a rate of like, let's see if I put it on there, about a centimeter for over several million years. So just by touching it like this, I'm probably wiping off 10,000 years worth of precipitation on there. It's one of the slowest processes we know on the planet. They're called manganese nodules because they often have a lot of manganese in them. And they also have other metals, and we've thought about mining them, but again, they tend to be out on the abyssal plain, so it's very expensive. As you see right here, 13 to 20,000 feet deep. It'd be very difficult to get to them. Volcanogenic marine sediments. Again, like I told you earlier, not much to say about this. When a big volcano goes boom, often the ash will go up in the air up to 20 miles high. And there isn't any rain to bring them down, so they basically spread out over the planet. And then as time goes on, eventually, you know, when it's calm enough, they'll settle out. That's one way we can tell, you know, huge, like supervolcanic eruptions in the past will have left sediments and lakes all over the world. Cosmogenic marine sediments. 60 to 300, this is an estimate, they can't go out and measure it, metric tons of cosmic ash or dust fall on our planet every day. Everyone wants to find a meteorite. Meteorites are pretty, depending on what kind they are and how rare they are, they're actually pretty expensive things, but most of it comes in the form of dust. And it gets laid down around the planet and ends up in the marine sediments. So we can tell things like big asteroid hits, because if there was a big asteroid hit and it vaporized the asteroid, which they usually get vaporized because they hit at about 20,000 miles per hour. Anyway, you would find, like the one that sort of wiped out the dinosaurs, you'd be able to find all around the planet the kind of stuff that was in that asteroid, and we call that actually the iridium layer. You've probably heard of it. Iridium is fairly rare, but not in asteroids. And there's iridium all around the world in a layer about 65 million years old when that asteroid hit.